Hello. So we just have a couple of extra problems from 16.8 to do using Stokes Theorem, and so we'll get started right away. In number 3, we use Stokes Theorem to calculate a line integral, where our vector field has components negative y squared, x, and z squared, and our curve C is given by the intersection of the plane y plus e equals 2 and the cylinder x squared plus y squared equals 1. So using Stokes, we have to write down what that means. That basically gives us permission to say that instead of using a line integral to calculate, I'm going to use a surface integral over S of the curl of my vector field dotted with ds hat. Okay, and if I use that, then the parts that I'm going to need, well, I'm supposed to take my curl vector and I need to evaluate it at my parametric function of my surface. And then the ds hat, that means I'm going to be dotting with r sub u cross r sub v, so that's the normal vector, and then dA. So this kind of gives me an idea of like the parts that I need to find. I need a parametric function for my surface, and then I need its first partials and the cross product of those, and then I need a dot product. And I also need the curl of my vector field evaluated at the parametrization. So there's a whole lot to find. But before I can do anything, I need to get the parametrization of the surface. So we need R of UV for the surface. But before I can even decide what my R of UV is, I have to figure out what is my surface. So that's the big question. What is my surface? Well, the best I can do right now is draw the region that I've been given. So they're telling me that C, my curve, is the intersection of the plane y plus e equals 2 and the cylinder x plus y squared equals 1. I could draw that. Let's see. I can draw my cylinder first, or at least part of it. It is a unit cylinder, so these are just ones. And I'm going to go out to 2 though, because I have this plane here. And the plane is going to kind of dictate to me where my cylinder ends. Okay, so the plane has a y-intercept at 2 and a z-intercept at 2, and we can connect those dots to allow us to kind of see what's going on here. Okay, so I'm not going to extend my plane out. I'm just going to have it there as a line for now, and that's going to tell me when to stop drawing my cylinder. So I'll go ahead and continue with my cylinder. All right, those are my stopping points. Okay, now if we take a round cylindrical figure and we slice it, we're not just going to have a straight line, we're going to have an ellipse, right? So we're going to get this sort of shape here, right? That'll be the top of the cylinder now. And that right there is actually giving us the curve of intersection. Now, if I was to look down on this curve, the counterclockwise direction would be like this. Okay, so this is C. It is the intersection of the plane and cylinder. Okay, so I need a surface. Now, the surface just has to be a region contained in the curve C. Okay, so let's just write that. The surface needs to be a region contained in the curve C. So that could be that the curve C closes off the top of a cylinder and we take the surface to be the whole cylinder, and then also the top. Or we could say that that elliptical shape that is contained in C, that's a surface. and that's good enough. So we have to always remember when we're trying to determine the surface that's contained in the curve C, that it doesn't actually matter what the surface is so long as it is contained in the curve C. And so I'm going to choose the region that's literally inside of my curve C. So the ellipse made from the intersection of the plane and the cylinder will work for the surface. Okay, so now we have to be able to look at that elliptical shape and realize, where did that come from? And this is where we have to really keep separate the surface from the bounds, okay? So the surface is the plane. Y plus z is equal to 2. It is bounded by the cylinder, and that's what's going to give us the shape. It won't just be some flat surface that goes on forever. We're going to use a cylinder in order to get the correct xy values that would give us that elliptical shape, okay? So when we parametrize, we don't consider the bounds, we only consider the surface. So to parametrize, only consider the surface. Bounds come later. Okay, well, that surface is a plane, and y plus z equals 2. I could solve for z. Z is equal to 2 minus y. And then I could say, well, let's go ahead and have a parametrization r of xy, where since we have an explicit function, z equals 2 minus y, that means x will get to be x, y will get to be y, and z will be 2 minus y. Now, x does get to play a part in this because on the plane, x is not 0. It's just that the plane is independent of x. It runs parallel to it. It doesn't mean that x is like not considered, okay? So we have to put in a placeholder for x, and now we have our parametrization. All right, the next thing that we need, looking up at our integral, we need to go ahead and find r sub x, r sub y, and the cross product of r sub x and r sub y. So let's do that. R sub x is equal to 1, 0, 0. R sub y is equal to 0, 1, minus 1. And then we need the cross product of that, so I'll draw my I, j, k over the top here. R sub x crossed with r sub y is equal to a vector with components 0, minus 0 in the first component. Minus in quantity, 1 times negative 1 is negative 1 minus 0. Third component, I get 1 minus 0. This simplifies to be a vector with components 0, 1, and 1. And this is indeed going to be a normal vector that points outward on our surface, okay? So that's great, we've got that. So this points outward and upward. Okay, so let's go back up to our integral. So far, whoops, that's not what I meant to do. So far, I've got my cross product. It looks like I still need the curl of my vector field, and then I need to take my vector field and plug in the parametric functions into my curl. So let's go ahead and find that curl of f. We will need to find a determinant, so we need the I, j, k in the first row, del x, del y, del z. in the second row, and then f has components minus y squared, x, and z squared. Okay. So in my first component, I have del del y of z squared, which is 0, minus del del z of x, which is 0. In my second component, I have a minus, and then in parentheses, del del x of z squared, which is 0, minus del del z of negative y squared, that's also 0. My third component, I have del del x of x, which is 1, minus del del y of negative y squared is negative 2y, so I'll end up with plus 2y finally. And then this just simplifies to be 0, 0, and 1 plus 2y. Okay, now what we need to do is notice that, let's see, we need to go ahead and we've already got things in terms of y's. We're good. So I'm looking at my curl of f, and what I'm supposed to do is everywhere there's an x, I take the x component of my vector function, my parametrization r of x, y, and I replace that in curl of f. So in my x and y components, I have 0. In my z component, I have 1 plus 2y. I'm supposed to take whatever y is from my parametrization, but in my parametrization, y is y. So curl of f of r of x, y is exactly the same. It's just 0, 0, and 1 plus 2y. There are no changes there. Okay, I need a dot product. Okay, just going back up to what we're trying to find, we need our integrand, and we need the curl of f dotted with the cross product of r sub u and r sub v. So let's go ahead and do that. So our final integrand is going to be curl of f dotted with r sub x cross r sub y, which will give us 0, 0, 1 plus 2y dotted with 0, 1, 1. This gives me 0 plus 0 plus 1 plus 2y. That's it. That's a simple integrand. All right, so now what we're working with is a double integral over d of 1 plus 2y dA. Okay, we have the integrand. This no longer looks like a surface integral because we have most of the pieces in it, but we need bounds. So if we go back up to our picture, the bounds that give this elliptical shape, like that's how we get this slice out of the plane, are coming from the cylinder, x squared plus y squared equals 1. So the bounds that give the elliptical planar shape are from the cylinder, x squared plus y squared is equal to 1. And so we should use those as our bounds for our integral, because those are going to give us only the x and y values that we care about. So that means we're going to look at a unit circle on the xy plane. And when we're dealing with a circle, that means we should use polar. And with polar on a unit circle, we know that r will go from 0 to 1, and theta will go from 0 to 2 pi. We know that x is equal to r cosine of theta, and y is equal to r sine of theta. And then we also know dA is equal to r dr d theta. So I'm going to take all those pieces and take what I need and put them into my double integral up above. So going back to my integral, double integral, I usually do my theta last, so I'll do 0 to 2 pi here. And I do my r first, 0 to 1. And then I have 1 plus 2y, which needs to be rewritten as 1 plus 2r sine of theta. And then my dA is r dr d theta. Okay, this is what we're working with. So we're back in polar coordinates, right? Like what we did in 15.3. So first I'll distribute the r. I get 0 to 2 pi, 0 to 1 of r plus 2r squared sine of theta, dr d theta. Integrating with respect to r, I get the integral from 0 to 2 pi of 1/2 r squared plus 2/3 r cubed sine of theta. And that's going from 0 to 1. And then when we're done with that, we'll deal with d theta. Evaluating r at 1 will give us something, but evaluating at 0, we get no contribution. So this will simplify to be 0 to 2 pi for the integral of 1/2 plus 2/3 sine of theta, d theta. All right, the antiderivative of 1/2 is 1/2 theta. The antiderivative of 2/3 sine of theta is going to give us negative 2/3 cosine of theta from 0 to 2 pi. The evaluation at 2 pi, I get 2 pi over 2 minus 2/3, because cosine of 2 pi is 1, minus the evaluation at 0, I get 0 minus 2/3, because cosine of 0 is 1. And it looks like those 2/3 are going to combine to give me nothing. I'm left with just pi for our final answer. Okay, so that's how we handle that one. That was kind of weird because we actually, in this particular one, it was questionable as to what the surface was. And you did have options, but you should always try to choose the simplest option. So if you can see that the closed curve C has a surface contained in it, and it's going to make life easier, use it. Absolutely. All right, the next example and last example is 4. And in problem 4, we're again told to use Stokes' theorem to compute the surface integral, where our vector field has components x, z, y, z, and xy, and our surface S is the part of the sphere x squared plus y squared plus z squared equals 4 that lies inside x squared plus y squared equals 1 and above the xy plane. And our curve C is counterclockwise when we get to it. Okay, so using Stokes, we all just kind of want to write that down. It's giving us permission to, instead of using this surface integral of the curl of f dot ds hat, we're going to look at the line integral closed over C of f dot dr. And what that means is we need an integral from a to b, so we'll need bounds for a t value. F will get evaluated at r of t, so we'll need a parametrization for our curve. And then dot dr becomes dot r prime of t dt. So now we can see the parts that we need. We need r of t to parametrize our curve C. All right, so let's see. We need C to be parametrized by r of t. But the first question to ask is, what is our curve? Well, the best way to answer that is to draw what we have. So we're given that we have a sphere above the xy plane. So that's a hemisphere. I'm going to draw this kind of big. All right, there's our hemisphere. Here's our XYZ octant. And this is a sphere with radius 2, so these are all crossing at 2's. Okay, now the next part of this is that there is a cylinder, a unit cylinder, and this unit cylinder this is not going to look its greatest, but please forgive me. All right, so what I have here, they're telling me S is the part of the sphere that lies inside of the x squared plus y squared equals 1. That is, if we can get a better picture of this region here. And there's our curve C, and here is our surface. How do I know that that's our curve C? Well, I'm looking at what I have drawn over here, and I'm seeing that the cylinder is going to cut through this sphere, and where it cuts through, there's going to be a curve of intersection, okay? So that's how we decide it. Our curve is the curve of intersection of the sphere with the cylinder. Okay, and that intersection is actually just a circle, and it's a circle defined by the cylinder. Okay, so C can be defined by the circle x squared plus y squared is equal to 1 at, well, here's the last part, at the level z where the intersection occurs. So I should say at the z level where the intersection occurs. Okay, so at this point, what we have here, we've got a circle of radius 1, so we could say, oh, okay, well, r of t has components. X will be 1 cosine of t, y will be 1 sine of t, and z will be, I'm not sure. It's a question mark. I don't know what it is. So I need to figure out at what z height or z level does the cylinder intersect the sphere. To find that, I just substitute the cylinder into the sphere. So that means in the sphere, I'm going to replace the x squared plus y squared with 1, because that's what my cylinder has for a radius. So I get 1 plus z squared is equal to 4. Z squared is equal to 3, and z is equal to plus or minus the square root of 3, but we're going to choose only the positive because we're above the xy plane. So now what we have is r of t is equal to the vector with components cosine of t, sine of t, and the square root of 3. Okay, I can't just let z be 0 because we are actually at a specific height for z. We're not on the xy plane. All right, now that we have the vector function that models the curve, what we need to do, let's go back up to our integral and see what we have. Okay, it looks like we need r prime of t, and then we need our vector field to be parametrized. Like we're going to substitute our parametrization in. So let's find r prime of t first. R prime of t will be negative sine of t, positive cosine of t, and 0. Our vector function evaluated at r of t will be, let's see, xz, so that will be square root 3 cosine of t. I'm just pulling the components from r of t. The second component of f is yz, so I'll have yz is the square root of 3 sine of t. And then the third component of f is xy, so that's going to be cosine of t sine of t. All right, next calculation, and then we'll have our integrand. F dot r prime is equal to negative square root 3 sine of t cosine of t plus square root 3 sine of t cosine of t plus 0. And all of that adds up to a big fat 0, which is fabulous, because now what we know is that our surface integral, double integral over s of curl of f dot ds hat is equal to a line integral from a to b of 0 dt, which is just going to be 0 for a definite integral. And so we're done. That was all we had to do. That's it. So that is the final example for Stokes theorem. Reach out if you have any questions at all.